All right, so the concept of subsequences will provide us a powerful tool in discussing the concept of convergence. So the idea is to construct a subsequence is as follows. So suppose you are given a sequence of real numbers, say an. One can construct a subsequence of this given sequence by omitting some terms of the sequence without changing the order of the remaining term. Now, the result is called a subsequence of an. So suppose you have a sequence of this like this. Let me try to define this informally first, and then I'll give you a formal definition later. Okay, so suppose we have a sequence like this. Okay, and where this is A1, this is A2, this is A3, this is A4, this is A5, A6, A7, A8, and so on. Now, one can construct a subsequence of this given sequence by essentially selecting some terms and then omitting others in increasing order. It's really important to have this selection occurring in increasing order. So, for example, all even terms of an and let's say all odd terms of an are subsequences of a sequence, right? So I can have a sequence like this, and I can choose to select every other. We'll skip this one, and so on, right? So that's an example of a subsequence. Or you can choose to select to make a different type of selection. Now, so to write a definition of this idea, consider that we are given a sequence an in which we perhaps delete certain terms and then renumber the remaining terms to get a new sequence, and let's say bn. So in other words, once I select some terms, then I can relabel this term and say maybe this is b1 and this now becomes b2 because it's the second selection. The third selection is b3, and then this is b4, this is b5, and so on. So the new sequence, which is obtained by selecting some terms of the parent sequence and omitting other in an increasing fashion, is called a subsequence. So in this case, bn, as constructed above, is a subsequence of the parent sequence an. Okay, all right, this is not a rigorous definition, so bear with me here as I try to maybe first strengthen your intuition of what a subsequence is before we formally define. Okay, so basically, a subsequence of a sequence xn is a sequence of some, but not necessarily all of the terms of the sequence xn. So also, based on our informal discussion, we've gathered that the terms appear in the same order as they appear in the parent sequence. Now finally, here is our formal definition. Let nk be a sequence of strictly increasing natural numbers. So that, by that we mean that n1 is less than n2, which is less than n3, of course, which is less than nk, and so on. Then the sequence x sub nk is called a subsequence of the parent sequence xn. As an example, let xn be a sequence of natural numbers such that xn is equal to n squared for every natural number n. Now, if we let nk to be equal to 2k, notice that the sequence nk is a sequence of natural number which is strictly increasing. Why? So the claim here is that the sequence nk is strictly increasing It's a strictly increasing sequence of natural numbers. Okay, so this is clearly the case since given k and let's say l, which are natural numbers such that k is less than l, and k is going to be equal to 2k, and l is going to be equal to 2l. Moreover, since 2k is since k is less than 2l, then I can multiply. Since k is less than l, I can multiply each side by 2. 2k is less than 2l, and this gives that nk is less than nl. So this is a sequence of increasing natural numbers. I'm sorry, this is a sequence, this is an strictly increasing sequence. Now, since for every k, which is a natural number, nk, which is 2k, is also a natural number, the claim holds. Right, so we indeed have a strictly increasing sequence of natural numbers. So now the point here is that, so we started with this sequence, which is a strictly increasing sequence of natural numbers. So then the new sequence x and k, which is obtained by taking 2k squared, so this is essentially going to be 4k squared, that's a subsequence of the. Okay, now let xn be a sequence of real numbers such that xn is equal to -1 power n plus 1 over n for every natural number n. Now, let nk be, let's say, 2k plus 1. Then I'm not going to prove this, but you can check at home that nk is a sequence of natural numbers which is strictly increasing. Okay, now if we compute x and k, so we'll have -1 power 2k plus 1 over 2k plus 1. Well, clearly, because 2k plus 1 is odd, then we get -1 plus 1 over 2k plus 1. Right, so that would be negative 2k plus 1 over 2k plus 1, which is, I guess, negative 2k minus 1 plus 1 over 2k plus 1. So we get negative 2k over 2k plus 1. In any case, this sequence, negative 2k over 2k plus 1, is a subsequence of the sequence -1 power n plus 1 over n. N is a natural number. Okay? All right, so the idea is because nk is strictly increasing, is a strictly increasing sequence of natural numbers, then automatically x and k. Important result in this lecture is called the Bolzano-Weierstrass theorem. In fact, it's an important theorem for our class. And essentially, the Bolzano-Weierstrass theorem says the following. If a sequence of real numbers is bounded, then it has to have a convergent subsequence. Well, so before I offer a proof for this result, let me give you an example of how surprising or in fact how powerful this result is. Consider, for instance, the following sequence. Let xn be a sequence given by xn is equal to cosine of n for any natural number n. Okay, so this is a pretty wild sequence. If you try to plot the terms of this sequence, it's going to be jumping around. It's going to be all over the place in between -1 and 1, right? So note that the absolute value of xn is going to be equal to the absolute value of cosine of n, which is, of course, less or equal to 1. Thus, xn is a bounded sequence. Now, this is clearly not a convergent sequence. It's not convergent at all. In fact, the behavior of the sequence is pretty wild. However, by virtue of the Bolzano-Weierstrass theorem, xn has a convergent subsequence. In other words, there exists a strictly increasing sequence of natural number nk such that, so in other words, there exists a strictly increasing sequence nk of natural numbers such that x and k, in fact, let me just rewrite it as cosine of nk is a convergent sequence. Subsequence of cosine of n. Okay, so that's a pretty remarkable property. It's a pretty remarkable result. So our objective in this video will be to, in fact, establish. Get going. Let us first discover a little bit of history. So the Bolzano-Weierstrass Theorem is named after Bernard Bolzano and Carl Weierstrass, and it's a fundamental result in real analysis. It was first proved by Bolzano in 1817 as a lemma, and then it was reproved 50 years later by Weierstrass. Okay, now regarding the proof. So first, let us start with, consider an a sequence. Let an be a sequence of real numbers which is bounded. Okay, now next we say that an has a peak if has a peak, and let's call this peak let's call such a peak a sub m. So we'll say that our sequence has a peak which will denote by am if am is greater or equal to an for all little n greater or equal to m. So as an illustration of what a peak might look like, so if this is let's say a representation of our sequence, so if at some point you have a behavior like this, and then it keeps going forever, right? So you can see, so let's suppose this is a1, and then this is a2, and so on. So for example, a2 is a peak, because if you move past a2, you'll notice that for any n bigger than 2, a2 is greater or equal to an, right? So a2 will be a peak. All right, so that's a little bit of illustration so you can understand what a peak really is. So we'll say that an has a peak, say am, if a sub m is greater or equal to a sub n for all natural numbers n greater or equal to m. Now there are two possible cases here. The two possibilities that we can have. It's possible for us to have infinitely many peaks, or we could have finitely many peaks, and those are the only two possibilities, right? Okay, so let us first assume, so for the first case, let us assume that the given sequence has infinitely many peaks. So we list the peaks by increasing order of the subscript. So we list peaks by increasing order of the subscript. So for example, we'll have a sub 1, a sub m2, and so on, a sub mk, and it keeps going in this fashion. Right, so this gives a construction of a subsequence AMK, where we'll have that AM1 is greater or equal to AM2, which is greater or equal to the next peak until we have some AMK, and we keep going in fashion. So essentially, we construct a new subsequence from the parent sequence, which is obtained by selecting the peaks. And since we have infinitely many peaks, of course, then we have a sequence. Now, there's a second case. So for the second case, let us assume that AN has a finite number of peaks. Say A sub M1, A sub M2, A sub M3, all the way till the last one, which is A sub Mk. So let us assume that we have k many peaks. As such, AMK plus 1, so the terms which is coming after the AMK, the mkth term, is not a peak by assumption. So we may choose some natural number n1 such that n1 is greater than mk plus 1, and on top of that, a mk plus 1 is strictly less than a n1. This is a simple consequence of the fact that amk plus 1 is not a peak. But also, a sub n1 is not a peak. Otherwise, it will be listed here, right? But it's not. So we may also select some natural number n2 such that n2 is greater than n1 and an1 is strictly less than an sub 2. And we iterate this process indefinitely, if it makes sense. To construct a sequence in fact, a subsequence ANK, where clearly AN sub 1 is less than AN sub 2, which is less than the next one until AN sub K, and so on. Right? So whether we in case 1, this case here, where we have infinitely many peaks, or whether we in case 2, we were able to construct a subsequence which is monotonic and also bounded, since the parent sequence is also bounded. So in either case, we have constructed a subsequence of AN which is monotonic and also bounded. Such a sequence must be convergent, because we know that any bounded sequence which is monotonic is convergent. And this completes the proof. So again, the big picture here is that if you're provided a bounded sequence, you can always find a subsequence of that parent sequence which is monotonic, meaning that it's either non-increasing or it is non-decreasing. And the fact that we also have boundedness allows us then to say that such a sequence has to be convergent. So our next result is the following. If xn is a sequence of real number which is convergent to some real number x, then any subsequence of xn will also be convergent, and not only that, it will converge to x as well. So let us prove this result. Let xn be a sequence such that the limit of xn when n is approaching infinity is equal to x. Next, let xnk be a subsequence of xn. By assumption, nk must be a sequence of natural numbers which is strictly increasing. Okay, so now let's epsilon be a fixed positive real number. By assumption, we may choose, or in fact, now we may choose, let me rephrase this a little bit. Letting epsilon be a fixed number, we choose some natural number n such that the distance between xn and x is less than epsilon whenever little n is bigger than. Okay. All right. Next, I claim that for any natural number k, nk is greater or equal to k. And I'll prove this, in fact, by induction. So indeed, proceeding by induction, we verify for the base case that if n is 1, then clearly n sub 1, as n sub 1 is a natural number, so a natural number is at least greater or equal to 1. So the base case holds. There's really nothing else to do here. Next, let us assume that nk is greater or equal to k for some natural number k where k is at least 1. Okay. As such, we'll have that n sub k plus 1, right, must be greater, n sub k plus 1 must be greater than nk, since nk is strictly increasing. Okay, so the fact that nk is strictly increasing allows us to say right away that nk plus 1 is greater, strictly bigger than nk. But then thus, or maybe consequently, nk plus 1 is going to be greater than nk, which is greater or equal to k by, and this is true by the inductive hypothesis. So, since nk plus 1 is strictly bigger than k, then nk plus 1 has to be at least k plus 1. Okay, so that gives us exactly the result that we want. We have thus proved that for any natural number k, if you're given an increasing sequence of natural number nk, then the kth term of that sequence has to be at least k. Okay, now moving on, if we choose some natural number k such that k is greater than n, since nk is at least k, which is bigger than n, it follows from our assumption, which assumption exactly? The fact that we chose here, we say that for fixed epsilon we choose big N so that it satisfies this inequality whenever little n is bigger than capital N. So I'm going to use that assumption here to then say that because nk is bigger than capital N, then the distance between x sub nk and x has to be less than epsilon. As a direct consequence of our results, the following is in fact immediate. If given a sequence xn of real numbers which admits two subsequences converging to two different limits, then the given sequence must be divergent, right? So the proof is more or less straightforward. We can prove this by contradiction. Let us assume by contradiction that there exists a sequence xn of real numbers which has two subsequences, let's say x l k and x n k, such that the limit of xlk when k is approaching infinity is not equal to the limit of x and k where k is going to infinity. All right, then such a sequence, I guess we can say the existence of such a sequence violates the results obtained previously. Which is that if a sequence is convergent, then it has to, so the point is that if a sequence is convergent, then every subsequence of that parent sequence must be converging to the same limit. As a result, let xn be a sequence defined as follows. Xn is negative 1 power n time 1 plus, let's say, 1 over n. Then note that x2k is going to be 1 plus 1 over 2k. I guess we can rewrite this as 2k plus 1 over 2k. And x2k plus 1 is negative 1, 2k plus 1, 1 plus 1 over 2k plus 1. And I guess that would be negative 1 plus 1 over 2k plus 1, which is going to be negative 2k plus 2 over 2k. Moreover, note that the limit of x2k when k is approaching infinity is going to be 1, and the limit of x2k plus 1 when k is approaching infinity is negative 1. So since x2k and x2k plus 1 convergent subsequence, subsequences of xn converging to different limit, then xn, the parent sequence xn, must be divergent. Okay, so the fact that we were able to construct a sequence, a subsequence, given a sequence here, we're able to construct two subsequences which are converging to two different limits, allows us right away to conclude that the parent sequence itself must be divergent. Let xn be a sequence of real numbers such that xn is equal to cosine of 2 pi n times 1 plus 1 over n. Now, let's suppose we choose x3k as a subsequence. Then this will be, of course, cosine of 2 pi times 3k over 3 times 1 plus 1 over 3k. And the outcome is we can move these two. So we have cosine of 2 pi k times 1 plus 1 over 3k. But cosine of 2 pi k is 1. So this gives us 1 plus 1 over 3k. And you can compute that the limit of 1 plus 1 over 3k, as k is approaching infinity, will of course be 1. On the other hand, if we compute x of 3k plus 1, then we'll have cosine of 2 pi times 3k plus 1 over 3 times 1 plus 1 over 3k plus 1, which is cosine of 2 pi 3k over 3 plus 2 pi over 3 times 1 plus 1 over 3k plus 1. And so this will then be cosine of 2 pi plus 2 pi over 3 times 1 plus 1 over 3k plus 1. Now, the fact that cosine is periodic allows us to get here that we obtain cosine of 2 pi over 3 times 1 plus 1 over 3k plus 1. Okay, now let's look at our unit circle here. Okay, so this angle will be 2 pi over 3. So its cosine is somewhere here, right? So remember that, okay, so pi over 3 is essentially 60 degrees. So cosine of pi over 3 is 1/2. So cosine of 2 pi over 3 is also 1/2. So what we have so far, going back to our calculation, we obtained that x of 3k plus 1 is equal to 1/2 times 1 plus 1 over 3k plus 1. And computing the limit of x 3k plus 1 as k is approaching infinity, we obtain 1/2 times 1, which is of course just 1/2. And the point is that x 3k, so x 3k and x 3k plus 1 are two subsequences of xn converging to different limits. Like we seen earlier, one is converging to 1 and the other is converging to half. Okay, as a result of the previous corollary, it follows that the given sequence cosine of 2 pi n over 3 times 1 plus 1 over n, this sequence here is a divergent sequence.